Okay, so this video is the final video in the trigonometry section of the geometry and measurement module. So the first topic was sort of a review of basic geometry, angle properties, volumes, surface areas, etc., and similarity. The second part of the geometry and measurement module is trigonometry, and we are just coming to a close with that here. And then the third part, which we'll move on to in the next sequence of videos, is circle geometry. And circle measurement, so arc length and areas of sectors and segments, etc. And that extends out to then some spherical geometry, so looking at what's happening with the planet time zones, latitude, longitude, things like that. So quite a bit more work to do, but this brings us to the end of the trigonometry. Okay, we're just going to work through some examples here. We're looking at problems in 3 dimensions, so we want to make use of our trigonometry, whether that's right-angled trig or non-right-angled trig. And the challenge here really is just in having the spatial awareness to being able to see the triangles that you're looking for. So you need to be able to isolate 2-dimensional triangles within the 3-dimensional problem. Okay, that's the key. So here we have a solid, it's a triangular prism. AEFD is a horizontal rectangle, so AEFD, so that rectangle there, so it's horizontal, so that's sort of sitting flat on, imagine it's sitting on a table or the floor, that's sitting flat on the ground. CF therefore is vertical, so this is a vertical rectangle going this way, and then we've obviously got a slanting rectangle going on the front here. Okay, so ABCD is a rectangle inclined at an angle of theta. Okay, so as I said, this is horizontal. This rectangle, therefore, is not horizontal. It is inclined at an angle of theta. Okay, so the angle of inclination or the angle of elevation is theta. AD is 32, so that's in the diagram. AE is 24, so that's that length, but that's the same as DF, so it's 24. And BE is 41, so that's this vertical height, which would be the same as CF. Okay. Find correct to one decimal place where necessary. We want to find all of these things. So the first thing we want to find is DC. Okay, so DC is this length here. So we want to work out, we want to, as I said, isolate 2-dimensional triangles that are going to allow us to do our calculations. So if we think about this right-angled triangle here, CFD, we want to find CD. We know CF, we know that's 41. It's going to be the same as that. And so actually, if we isolate that triangle there, we've got CF, and that's 41. That's theta, and that is D, and so this is 24. And we want to find CD. Now, we're finding a length. We know the other two lengths. This is just a straight Pythagoras. So DC is the hypotenuse, so DC squared will equal 24 squared plus 41 squared. So 24 squared plus 41 squared is 2257, and so therefore DC is the square root of 2257, which is approximately, and what do we want? 1 decimal place where necessary. So the where necessary just means if it's an exact value, we don't need to give a rounded answer, but where we do need to round it should be to 1 decimal place. So 47.5, and that's a length, and the lengths are in centimetres. Okay, part B, we want to find AF. Okay, so AF is this diagonal length along the horizontal base. Okay, so we want to think about perhaps this triangle. All right, or we could obviously have drawn the one up here. It's the same. So that's a right angle down there because it tells us it's a rectangle on the bottom. So we know that's a right angle. Okay, so we know, let's see what we know here. That's F, that's A, that's D. We know this is 24, we know this is 32. Okay, so I'm just going to use Pythagoras again here. So AF squared is 32 squared plus 24 squared. 32 squared plus 24 squared is 1600. And so, AF is the square root of 1600, which I suspect we'll find is a very nice 40. So no need to round there, that's exactly 40 centimetres from A to F. Okay, so then we want angle CAF. So we're going to need a triangle in which we have C and A and F. So now we want to think about C to A to F. It's a triangle that's standing up in the middle of this shape. That's a right angle in there. Okay, so if I draw that out, okay, so which triangle's which? That's C and that's F and that's A. Okay, so CAF is this angle in here. That's what we're trying to find. C to F we know is 41. We've got that originally in the diagram. A to F we've just worked out in part B, and that's 40. And so therefore we can find that angle CAF, which is this angle in here, using tan. So tan of angle CAF is equal to opposite, which is 41, over adjacent, which is 40. And so angle CAF is inverse tan of 41 on 40. Let's work that out. Inverse tan of 41 on 40. Pretty close to 45, yep. And what do we want again? 1 decimal place. So 45.7 degrees. Okay, so it's really just being able to, as I said, identify a two-dimensional triangle. Draw that out separately if you need. Be clear about what lengths and angles you know in that triangle, and then work out whether you're using Pythagoras, whether you're using SOHCAHTOA because it's a right-angled triangle, whether you're using sine rule or cosine rule, whatever it might be. Okay, example 2. Dylan and Eugene are both looking at a tower of height 35 metres. Dylan is standing due south of the tower, and he measures the angle of elevation from the ground to the top of the tower to be 15 degrees. Eugene is standing due east of the tower, and he measures the angle of elevation from the ground to the top of the tower to be 20 degrees. Find correct to 1 decimal place. Okay, now the problem here is being able to draw a diagram where you can see everything that you need. So as we saw in this previous question where we had the diagram, you need to use elements of perspective. Okay, so this here is horizontal. Okay, and this here is vertical, and we need to draw it that way so that we can also look at this horizontal direction and we can see in 3 dimensions. So for example, here if we just focused on the tower and Dylan and Eugene, we know that, don't draw this, but we know if we've got the tower here, we know that Dylan is due south of the tower and he's, we don't know the distance, and we know that Eugene is due east of the tower. And again, we don't know that distance. But what we do know is the height of the tower, which is coming straight out of the computer screen at us. Okay, so this diagram's not helpful because we know the height of the tower, and we also know some angles of elevation. I'm motioning my pen away from the computer screen, but we also know some angles of elevation up to the top of that tower. Okay, so we sort of need to be able to think in perspective. Now we could draw it this way. My perspective doesn't work very nicely that way. I would tend to stick with east-west, still going horizontally. I would draw north-south going on some sort of angle this way. Okay, and that means that we now have the space to draw vertical, going straight up and down. Okay, up, going up. Okay, so let's have that this is our tower. Alright, so we know that the distance, so that's the base of the tower at T. I'm going to call it maybe I'll call it X here in the middle, it's the centre. Let's call that T for the top of the tower. We know that the tower is 35 metres tall. Okay. We know that Dylan is somewhere due south of the tower, and that the angle of elevation from the ground to the top of the tower is 15 degrees. Now I don't think I've drawn my diagram to scale, but that's okay. Okay, that's up and down and horizontal, so that's a right angle in there. And angle of elevation, so this angle here is 15 degrees. Okay. Now we also have Eugene, who is due east of the tower. He's somewhere over here. And his angle of elevation to the top of the tower is 20 degrees. So actually, Oh no, my diagram's okay. That is 20 degrees, and that's a right angle. Okay, so we want to know the distance from Dylan to the foot of the tower. Okay, so that is d to x. Okay, so that is this distance here is what we're finding in part A. Alright, so that's what we're finding in part A. If we focus on that purple triangle, okay, we know that's 35. We know that is 15. And we're trying to find dx. Okay, so we've got opposite and adjacent, so we're going to use tan. We know that tan of 15 degrees is opposite, which is 35, over adjacent, which is what we're trying to find, dx. So dx times tan of 15 is 35, which means dx is 35 divided by tan 15. And we want our answers to one decimal place. 35 divided by tan 15, control enter, to one decimal place, that is 130.6, and it's a distance and the units are in meters. Okay, then we want the distance from Eugene to the foot of the tower. Okay, so this time we want, this distance in the orange triangle. So let's think about that. We know that that's 20 degrees, that's a right angle, that's 35, that's the top of the tower, that's the bottom of the tower, and this is Eugene. So we want XE, and again we're going to need tan. Tan of 20 degrees is opposite, which is 35, over XE, which means XE times tan of 20 is 35, which means XE is 35 divided by tan of 20 degrees. Let's just edit this previous calculation, it's just changing the 15 for 20. Control enter, to one decimal place, that is 96.2 meters. Okay, and then finally in part C, we want the distance between Dylan and Eugene. So we want this distance flat on the ground. Now again, remember that this is north-south, this is east-west, that's a right angle in there. Okay, so we've got another right angled triangle there. So again, let's focus on drawing out that triangle. We've got X, which is the bottom of our tower. We've got Dylan down here, and we've got Eugene over here. We want to find the distance between them. That's a right angle. We know X to E is 96.2, and we know D to X is 130.6. We're trying to find DE. We've got two lengths in a right angled triangle, so we're going to use Pythagoras. DE is the hypotenuse. DE squared is 96.2 squared plus 130.6 squared. Now remember, we don't want to use rounded answers to then create more rounded answers, so no reason not to work exactly with our CAS. We're going to do that squared plus this answer squared. Okay, and that's, that's 26309.12. And so DE is the square root of that, which is approximately square root of that number there. Now we give our answer to one decimal place, 162.2 meters. And that should make sense, which it does. It's bigger than both 130 and 96. It's still within the vague vicinity of those numbers. It's not a crazy, nonsensical answer. So we're all good. All right, then we want the bearing of Dylan from Eugene. So remember, the from is what's important. From Eugene. So if we are Eugene, facing north, turning clockwise, how do we get to Dylan? So that is the angle that we need. And so therefore, I'm going to work out that angle in there and then take that away from 270 to work out the bearing. Okay. So we're going to need tan. We've got opposite and adjacent, although we've also got hypotenuse now with this one, so you could use any of your trig ratios. I'm going to use tan. So tan of theta is opposite, which was the 130.6, over adjacent, which was the 96.2. So theta is inverse tan of 130.6 over 96.2. Let's work that out. Inverse tan of this one up here divided by this one here. Okay, and we find that that is 53.6 degrees. And so therefore the bearing, and we're not told anything different here, we will still want one decimal place. And so therefore our bearing, as we said before, is going to be 270 plus theta. So that is 270 plus 53.6, 270 plus this nice exact answer here, and giving our final answer to one decimal place, the bearing is 323.6 degrees. Oh, that doesn't make sense. Sorry, it's not 270 plus theta. Okay, that's where that does my answer make sense. It's 270 minus theta. So we know it would be 270 to go the whole way around here, minus theta is going to give me that red bearing. So sorry, let's do that again. That's that important moment of does my answer make sense. So sorry, it should have been 270 minus 53.64, so let's get rid of that. It's better. 216.4. Okay, and then example 3. From the top of a cliff that runs north-south, the angle of depression of a yacht, sorry, that should be a comma, 200 metres out to sea and due east of the observer is 20 degrees. Find the height of the cliff correct to the nearest metre. Okay, so we've got our cliff. Let me get my information right. We've got our cliff. We've got, so the cliff is actually sort of running, obviously a cliff is not just, it runs north-south. We've got water heading out to sea. The cliff runs north-south, but that's actually a bit irrelevant. So if that's, so what we're essentially saying is, oh, actually it's not, that's north and that's south, and so therefore this is east and this is west. Okay, so you've essentially got north, south, east, west happening here. Okay, so the yacht is due east, so we're going straight out this way, so that's a right angle, and it is 200 metres out to sea. The angle of depression of a yacht 200 metres out to sea and due east of the observer is 20. So the angle of depression is 20. So remember, the angle of depression is relative to horizontal. So from that, we either work out that this angle in here, in the triangle, is 70, or we use the alternate angle to say that that means that this angle down here is 20. We want the height of the cliff. That's what we want. Right, so it's a nice straightforward right angle triangle trig problem. It's tan again. So tan of 20 degrees is h over 200. And so h is 200 times tan of 20, which is, tan of 20 to the nearest metre, 73 metres. Okay, so the cliff is approximately 73 metres tall. When the observer next looks at the yacht, he notices that it has sailed for 150 metres parallel to the cliff. Find the horizontal distance between the yacht and the observer when it is in its new position. Okay, so what we're now seeing is that this is the direction of the cliff. The yacht is sailing parallel to that. Okay, for another 150 metres. And then what we want to know is to find the horizontal distance between the yacht and the observer when it's in its new position. So we are going to want that distance there. For this question, we can actually now look at this from a bird's eye point of view. Okay, because we don't actually need that vertical distance for part B. So if we think about this as a bird's eye point of view, so I'm going to mark that, that's my observer up there. Okay, if we look at this from a bird's eye point of view, there's my north-south cliff. There's my observer. I'll put him down here just so we can fit everything in. We've got the yacht that's 200 meters out to sea, but it is sailing in a direction that's parallel to the cliff, and it is sailing 150 meters. And now what we want to know is the horizontal distance. Everything in this diagram I've drawn in part B is horizontal because I'm looking at a bird's eye view. We want to know the horizontal distance, so that's the yacht. So this is the yacht at position 2, this is the yacht at position 1. Okay, so that's the yacht at position 1. We want to know the horizontal distance between the yacht after it's sailed and the observer, so that is that distance there. That's a right angle because this was north, south and east, west. And so we can just use Pythagoras to work out x. So x squared is 200 squared plus 150 squared. So 200 squared plus 150 squared is 62500. And so x is the square root of that. Control enter. Oh, it's exactly 250 meters. Give your answer to correct the nearest meter is actually not needed there because it's a perfectly correct exact answer. Okay, find the angle of depression of the yacht from the top of the cliff when it's in its new position. Okay, so now we sort of need to combine together these two diagrams and think about, because the vertical now is important. So remember, the yacht's now sailed up here by 150 meters. It's now here at position 2. And we know that that horizontal distance there is 250 meters, and we want the angle of depression. So we want to think about a vertical triangle there. Okay, so we're now essentially going to have our observer at the top of the cliff, the base of the cliff, which we haven't given that point a name, to yacht 2. Okay, so let's just call that, we're talking about that point there, let's call that x. So this point here in the bird's eye view diagram, O and X are the same position, okay, because they're they're on top of each other. Okay, so we know the height of the cliff. We worked that out in part A. It's approximately 73. That was a rounded answer, so I'm going to use that nice exact value when I need it. We know that the distance from X to yacht 2 we found in part B, and that was exactly 250 meters. So I'm actually going to write this as what was it? It's on my CAS up there, 72.8, just to remind me to use a more exact value. And we want to know the angle of depression. So that is from horizontal, that is what we want to know. Okay, and so to find that, I'm either going to find this angle down here, which is the same angle, or we could have found that one in there and taken away from 90. Alright, so the angle of depression is theta. Let's therefore find this theta down at the bottom right of the triangle. And so again, it's tan. Tan of theta is the opposite length, which is 72.8 over the hypotenuse, the adjacent length, which is 250. And so theta is inverse tan of that. Inverse tan of this exact number up here divided by 250 was exact, so I can just type that. And so theta, the angle of depression to the nearest degree, is approximately 16 degrees. Okay, so as I said, it's still just often two-dimensional trig, often right-angled trig, although sometimes we might need sine rule, cosine rule, but it's really just about getting your head around which triangles are relevant. Drawing diagrams, drawing repeated diagrams, thinking about the angle at which you're looking at the diagram and how the different diagrams connect to each other. Okay, so exercise 18F is the work for today.